Hello everyone and welcome to another video. I'm very excited today because this is the first discussion in our extensive series of videos focusing on ordinary differential equations. I really like ordinary differential equations because you see them so often in all different aspects of science and engineering. For example, if you do any work with, say, controls, dynamic systems, flight mechanics, you'll see ordinary differential equations pop up time and time again. And today what I want to do is just introduce what is an ordinary differential equation, or ODE, and talk about how you might recognize them and how they show up in different systems. And then we will talk about where we're going in this extensive series of videos at the end. So to start, let's just talk about ordinary differential equations. And maybe the thing that makes this different from what most people have seen is this word differential, right? If we took out this word differential and you just said ordinary equations, why don't we start there, right? What is an equation, right? An equation will obviously has an equal sign on it, right? And we are trying to make a left-hand side equal to a right-hand side. So a typical equation, I don't know, you might have something like, let's make something up. How about x squared plus 2x on the left side? And then on the right side, I don't know, let's make something else up. How about 3x plus 2? Right? So here you go. Here is an ordinary equation. Now, what are you trying to do with an ordinary equation, right? You are trying to make the left-hand side equal to the right-hand side by tuning some knobs or changing some parameters. So in this case, it appears that the variable that we're able to choose here, or the thing that we have to solve for, is this variable x. So I guess the easiest way to maybe think about this is obviously just plot this thing. Right? If you were to just graph this of just x versus basically f of x, right, or what it evaluates to, let's plot in blue the left-hand side. So the left-hand side, I don't know, it's going to do something like, maybe, that's maybe not super accurate, but here, let's call this the left-hand side, right, for this expression. This is the left-hand side. Okay, and then in another color, I don't know, how about red, let's make the right-hand side another plot. So the right-hand side, if you plot this thing out, it would look something like, well, it's just a line, right? It's something like, I don't know, I'll make that up. Right? So red is the right-hand side. Okay? So what we're doing in this equation, again, is we're looking for the value of x where the left-hand side equals the right-hand side. And you can kind of graphically pick that off here and here. And numerically, I think this comes out to, this is positive 2 and minus 1, right? And we can verify that these values of x, right? So we've discovered that there are two solutions to this, right? So x is a set of solutions of minus 1 and 2, right? They're these two single points that we claim satisfy that equation, right? So let's just check. So let's plug in our solutions into the left-hand side. So let's do this first one of minus 1, okay? So we have minus 1 squared plus 2 times minus 1. That better equal the right-hand side. What do we have on the right-hand side? This is 3 times minus 1 plus 2. So again, you just work this out. I don't know, 1 minus 2 has got to equal negative 3 plus 2. So here, minus 1 is equal to minus 1. Yay, check, that works out, okay? So we see that, yes, this value satisfies. It makes the left-hand side equal to the right-hand side. So again, we can do the exact same thing for the second one if we really want to. So this just becomes a 2. This is a 2. This is a 2. So carrying this out, this is now a 4 plus 4 on this side. And then this becomes, yeah, sorry, this is pretty boring math, but I think everyone, you'll see why this matters in a second. Okay, so yeah, in this case, we get 8 is equal to 8, right? So yay, that all works. So again, nothing mind-blowing here with a normal equation. Now, let's go ahead and reinsert this word differential, right? What does that mean here, okay? So again, keep in mind, with our equations, all we're trying to do is make a left-hand side equal to a right-hand side, okay? So let's look at an example of what does an ODE look like, or an ordinary differential equation, right? We know what an ordinary equation looks like. What does this differential bit look like? So it's similar, except now instead of searching for a single value of x, what we're actually looking for is we're going to start looking for functions, an entire function that makes a left-hand side equal to a right-hand side. So let me give you an example of this. So an example of an ODE. So again, I'm going to start abbreviating these things ODE instead of having to write out ordinary differential equation. ODE is the same thing, okay? So let's make this up. So again, what we're looking for is you might have a function now. So x, this is not a single value anymore, it's a function. So to denote that, I'm going to write this as x of t, right? So this is a function which has an independent variable t and a dependent variable x. So in other words, what this thing looks like, I'm going to just make this up. So instead of a single point, right, instead of a single number, I'm looking for some function. Who knows what this thing does? Maybe it does something like this, right? Where at every value of the independent variable t, you have a value of the dependent variable. So I'm looking for this entire function. Now, this right now is pretty boring. This is just the function itself. Now, what makes this interesting is this differential part. If you have, maybe I'll put the equal sign here. I'm going to work on this left-hand side. This left-hand side might have the function itself, but then I also have to satisfy, maybe I need like the derivative of the function, like such, right? So this is the derivative of the function with respect to the independent variable. And in this case, there's only one independent variable, which is t. T is typically time, but we'll get to that in a second, right? So you might have the first derivative. You know what? You might even have the second derivative, like d squared x of t dt squared, right? And now you might not just have to add all of these together by themselves. There might be coefficients in front of these, like maybe there's a constant a plus b plus c. Okay, so now can you see how this left-hand side now is now a equation, right? But it's a differential equation in the sense that the thing I'm searching for is x, right? And now I don't just need x, I need its derivative, and I need its second derivative, and I need all these linear combinations of them to add up to something. Well, it has to equal something like, I don't know, what's the right-hand side? So we said that this left-hand side, this is going to be a function, right? It's not just a single value. So the right-hand side also should be a function. So typically, let's make something up. Let's say this is like g of t, some other function of t, right? Okay, so this is an example of an ordinary differential equation, and in fact, this is actually more special. This is an example of a linear ordinary differential equation, and we'll contrast this later with a potentially nonlinear differential equation, all right? So this is what it looks like. So again, the thing we're looking for, again, all we're trying to do, it's still an equation. I want to make the left-hand side equal to the right-hand side, but now the left and the right-hand sides are functions, right? They're not just single values like we saw earlier. It's an entire function that we're searching for, okay? Now, let's make another note. Another thing you may note in terms of notation, you may see, and in fact, I'm going to use this quite a bit, instead of having to write dx of t dt, this is a little bit tedious. What you may see is x dot of t, right? So a single dot means a single derivative. So likewise, a second derivative of this function, dt squared, right? This is going to be x double dot of t. Okay, so an alternative way to write this same ODE using the dot notation, which is a lot more common, is you may see this thing written as ax double dot of t plus bx dot of t plus cx of t has got to equal g of t. Okay? Now, one more thing that we should mention while we're talking about just general examples of this function, we're going to see later that there are a family of different functions that are going to satisfy this, right? There's not just a single unique function x that will make the left-hand side equal to the right-hand side. There's actually a whole group or a whole family of these functions. So a lot of times, in order to narrow down the solution space, we also are going to have to put some restrictions on what does this x, what is it able to look like? So one thing that may happen is we may add what are called initial conditions. Sometimes maybe you might hear these also referred to as boundary conditions. Okay, so all that's saying is this function that I'm searching for, it has to be at certain values at certain locations, namely, usually it's the initial time, like here at time 0. We want to say that, okay, this function, it has to start like up here. Like here is x at time 0. So this function down here that I just drew, while it might satisfy this overall differential equation, it will not satisfy this initial condition because I need something that's going to start. The function has to start here. So maybe it's got, and furthermore, maybe it also has to have a specific slope to start with, x dot at time 0, right? So something like this red, might be a function that satisfies both this differential equation as well as initial conditions. So a lot of times to fully specify the problem, we're going to say that the function that you're looking for at some time, typically that time is time 0. This has to equal some value, okay? So all this is just saying this is your initial position if you want to think about it, and then the x dot at time 0, the initial velocity or the initial slope of that function has got to equal some other number. Right? Now usually these are given to you, right? They're initial conditions or boundary conditions of the problem. So overall, this is an example of a linear ordinary differential equation fully specified with 2 boundary conditions here, okay? So we're going to look over examples of this. In fact, why don't we do this right now? Give me a second to erase the board and we'll look at an example of solving this. All right, so here's an example of a linear ordinary differential equation. So x double dot plus 3x dot plus 2x to t has got to equal 4 minus t plus t, 3t squared, okay? So again, you see this right-hand side, this is just a quadratic, right? But now I'm looking for a function now x, such that when I take its second derivative, add it to 3 times its first derivative, plus 2 times itself, it equals this quadratic function here, okay? And furthermore, we've got these 2 boundary conditions here that I need the function to start at 3 and its initial slope has to be -2, okay? So that's what an ordinary differential equation looks like. So now what you're probably asking is, what is the solution to that differential equation? Well, that's what we're going to get into in this series of discussions, okay? So further on down the road, in fact, I'll show you exactly how to solve this exact equation, this differential equation. But for now, let me just pull out a thin air and why don't you take my word for it that this is the solution, okay? It's this function here, which it looks a little wonky, right? It's got exponential terms. It's got some other, it almost looks a bit like a quadratic, but it's not the same quadratic that's up here. So this is actually what the solution looks like, right? And again, I'll just flash up a screenshot of the plot of this function so you can see what it physically looks like. And again, the point to remember here is we're searching for a function, right? So this x of t, you see, it's not just a single point, right? It's an entire function that is defined for all values of t, right? So what we need to do now is we should ask ourselves, does this actually work, right? Does this make the left-hand side equal to the right-hand side? So the way we're going to check that, right, is what I should do is I should take this and plug it into the left-hand side and see what we end up with, right? And I want to make sure that it ends up with the right-hand side. So to do that, you're going to see we're going to need x dot. So maybe we should compute that right now. So let me write down what is x dot of t, right? So just take this thing's derivative, right? So what is this? This is minus 4e to the minus 2t plus 7e to the minus t. That goes away. We end up with minus 5 plus 3t. Would everyone agree that's x dot? We're also going to need x double dot, right? So x double dot of t is going to be, I guess I'll take this thing's derivative again. So this is 8e to the negative 2t minus 7e to the minus t. That goes away, plus 3. Okay, there we go. So now all we have to do is let's go ahead and check what is the left-hand side, right? So basically I need to take x double dot. So I take this thing right here, right? I take 8e to the minus 2t minus 7e to the minus t plus 3, right? Would everyone agree this here is x double dot, right? Okay, now I need to add this to 3 times x dot. Well, that's this thing right here, right? Minus 4e to the minus 2t plus 7e to the minus t minus 5 plus 3t, right? So this thing in brackets is x dot, right? And then I need to add this thing to 2 times the whole thing, which is, oh, yuck, ran out of space. Tell you what, let's just put it in here, right? Just put in this original thing, right? I'll just write a couple of these terms. 2e to the minus 2t minus 7e to the minus t plus yada, 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 right? All this other junk, I just ran out of whiteboard space, right? This thing in brackets is x, okay? So now you can see it's just algebra at this point. So I'm just going to skip all that boring algebra. I'll let you go ahead and collect all of these terms. And at the end of the day, what you're going to end up with is this boils down to 4 minus t plus 3t squared. right? Which is perfect because this is the entire left-hand side, right? And if you look, this left-hand side does in fact equal the right-hand side. So yes, check. This solves the ordinary differential equation, right, that we started out with. Now, let's go ahead and check the initial conditions, right? I need to make sure that this solution we propose here matches the initial conditions. So what I need to do is I need to look at where does this function start at. So in other words, I need to evaluate the function at time equals 0. Well, let's just take this thing, right, e to the minus 2, and now everywhere you see a t, plug in a 0, right? So minus 7e to the minus 0 plus 8 plus 5 times 0 plus 3 halves times 0 squared, right? So gone, gone. This turns into, basically this whole thing turns into minus 7. Tell you what, let's just write this down here. So this is 2 minus 7 plus 8. What does that equal? 9. Did I do this wrong? Wait a second. That's 10 minus, no, this equals 3, right? So x of 0 is equal to 3, right? So the function at time equals 0 equals 3, which, again, matches up with our specified initial condition. So check mark, it satisfied that initial condition. Let's check our last one, right? X dot at time 0. Okay, so again, that means take x dot, this function right here, evaluate it when time equals 0. So we end up with minus 4 times e to the minus 2 times 0, plus 7 times e to the minus 0, minus 5 times 0. No, sorry, no, that's just a 5. That's just a 5 there, plus 3 times 0, right? So, okay, what do we end up with here? Minus 4 plus 7 minus 5. That's, wait a second. Did I do this wrong? I think I got too excited here. Where did I get? This is minus 4 plus, that is, yeah, plus 7 minus 5. Yeah, that's right. Shouldn't this come out to minus 2? Oh, wait, hold on. I think it does. I think I'm staring. Yeah, 9 minus 7. Yeah, this is minus 2. Yeah, negative 9, negative 2. Good. X dot is 0. Good. That checks out because that's what we're looking for over here. So there we go. That worked, okay? So again, this hopefully gives you a flavor of what is an ordinary differential equation, how can we check that a solution matches the differential equation and matches the initial conditions, okay? So this was an example of a linear ordinary differential equation. You don't just have to live in the linear world. In fact, a lot of times differential equations become nonlinear. So give me a second to erase the board and let's look at an example of a nonlinear ordinary differential equation. All right, so here's an example of a nonlinear ordinary differential equation. If you look, it looks similar. The differential equation part, you still have an x double dot, x dot, and an x here, but the coefficients of x, right, they're not constant numbers anymore. In fact, they're the independent parameter, and in fact, it's not even nice. It's right. This is the product of the second derivative of the function with the independent variable squared, right? Here's a product x dot with the independent variable, and here again, so again, you can see how this is a little bit more ugly, right? And this makes it a nonlinear ordinary differential equation because these coefficients are not constants. So what's interesting about this is actually a very famous differential equation. This is called Bessel's equation. Interesting side tangent. This actually shows up when you're studying partial differential equations, but again, that's a complete other discussion for which we actually have another series of videos to talk about, but I don't want to muddy the waters too much. Just look at this as an ordinary differential equation because that's what it is. It just happens to be nonlinear, okay? So in this case, Bessel's equation has this parameter v, and this v is typically, it's a real number which is greater than or equal to 0. Now, if it's also an integer value, right? If you only consider v's that are integers, actually you can show that the solution or the function that satisfies this differential equation is given by this crazy function. So this is called one of the Bessel equations or a Bessel function of the first kind, okay? So these actually have a very special name. Sometimes these are referred to as j sub n of t here. So these are, again, they're called Bessel functions of the first kind, and again, we'll talk about these a little bit later. All we want to think about and just realize is that now when you have a nonlinear ordinary differential equation, you can see how the solution can get a lot more complicated, right? And again, just for giggles, why don't I go and show a screenshot of what this function looks like for n equals 0, n equals 1, n equals 2. Again, to just show you that for a single ordinary differential equation, you could have multiple multiple solutions which all satisfy the differential equation. And as we talked about earlier, we're going to use initial conditions or boundary conditions to kind of whittle down the space of which solutions satisfy both the differential equation and the initial conditions. To make it even more interesting, this is Bessel functions of the first kind. There are Bessel functions of the second kind, which are even more complicated. And again, I don't want to get into that because I think that's just going to muddy the waters. I'll just show a screenshot of some of these solutions of what they also look like. Again, just to illustrate the fact that there are more than one ways to skin this cat, right? There are more than one type of function that can possibly satisfy a differential equation, and that's what gives them a lot of their richness. Now, in general, maybe what we should think about is what a differential equation looks like, right? Or what an ordinary differential equation is really going to look like. It's going to be some function, I don't know, let's call this capital F, right? And this is going to be a function of obviously the independent variable t, but then what made it a differential equation is the fact that there are the dependent variable x of t in here, as well as potentially derivatives of it, right? This is where the differential part came in, right? All the way up to, who knows, x to the, and maybe I'll write, sometimes you'll see, I'll tell you what, I should have written it using the ddt term, but I'll write it here. How about using ddt notation? Right, all the way up to the nth derivative of this thing, right? And this thing equals typically a right-hand side. This, you know, you could write this as 0. You know, if this was non-zero, you could subsume it into this capital F. So this is the general format of a differential equation, right? With a ordinary differential equation, right? It just looks like this, right? This is what the ODE looks like. Okay, so maybe now that we've talked about just the mathematical ideas behind the differential equation, you might be thinking, you know, well, is this just some random mathematical curiosity? And no, in fact, like I said earlier at the beginning of the discussion, these show up all the time in physical systems. So let's go look at a few of those right now. All right, so here's an example of an ODE, namely, how about this ball? If I just sit here and I maybe toss it up and then let it fall. Now, you might ask, okay, sure, that's a physical situation, but how in the world does that possibly turn into an ordinary differential equation? Well, what we should probably do is just go ahead and model this ball and look at what are the equations of motion that govern its behavior. So why don't we just go ahead and say that, okay, here's a ball with mass m, and we're going to measure the deflection or the distance that the ball travels as something like this. So here's x, right? X is going to be the position of the ball from where we start. We showed that the ball, when we threw it, it kind of started with this initial upward velocity here. So it started with x0 dot, right? It also started at this particular position. I guess we could call that x0, right? Some distance. In our case, I think it was 0 because that's where we kind of threw it from. But anyway, long story short, this is what's going on. And then we saw the ball kind of arc up and then fall down in a very classic trajectory problem, right? And I'm sure you're saying, okay, sure, I learned how to solve that or what the equation was for that in high school physics. Let's see, where does this come from an ordinary differential equation perspective, right? Well, what we should probably do is, like we said, write the equations of motion for this ball. And I think you'll all agree that this ball, since we're sitting here on Earth, is subject to force is equal to mass times acceleration, right? So for a constant mass system, Newton's second law basically boils down to F is equal to ma, right? Okay, what are all the forces on this ball? Well, I don't know, let's just start drawing those maybe in blue. Pretty simple. I think the way reinforced that was acting on this ball is gravity, right? Which has a magnitude mg. So the force is what? It's mass times gravity, right? It's just a constant force pulling down all the time is equal to the mass times the acceleration. Well, what's the acceleration of this ball? The acceleration of the ball, if I have the position of the ball as x, wouldn't you agree that the acceleration is x double dot of t? So here you go. If you look at this thing long enough, here is our second order, actually linear ordinary differential equation, just like we saw earlier. So this is an ODE, and luckily for us, it's actually a linear ODE. In fact, we can solve this thing pretty simply because it is so easy, an ODE. We could basically just do this, right? And then we're gonna integrate both sides from 0 to time t. The current time, and I guess we got to change this index here. Instead of t, let's use tau, d tau, just so we don't confuse our index of the variable of integration with our upper integration limit. So, okay, what do we end up with? This side turns into just gt, and then this side turns into, I think you would agree, that's x dot at time t minus x dot at time 0. Right? Okay, great. Let's do this again. Let's integrate both sides from 0 to time t, 0 to time t. Again, we got to change our variable of integration. Let's call this tau d tau, right? And then same thing. This is d tau, and I got to change this one to a tau, right? This is just a constant. So what do we end up with on this side? We end up with 1/2 gt squared, right, is equal to x at time t minus x at time 0, right, minus x dot 0, t, right? There we go. Okay, great. So I think we can move all of these to the other side, and we end up with our function that we're looking for, x of t. This is just 1/2 gt squared plus x dot 0 t plus x 0, right? So again, here we go. Here's our solution with that satisfies specific boundary conditions. So here we go. This is one way you can solve this, and you can see an ordinary differential equation popped out of this system. Now again, this is not a terribly interesting ordinary differential equation. Where it gets more interesting is, what if we were to add different types of forces or different types of effects on this ball? So for example, we know that this ball, it didn't fall through a vacuum, right? This equation is valid for a vacuum. Well, it's falling in air, right? The air has some drag force to it, right? Any of you that are aerodynamicists or work with aircraft or anything, or fluid mechanics people, know that there's a drag force on this, right? There's like an F drag. Right? So this drag force, I don't know how you want to model this. We can pick some way. Why don't we say that the drag force is linearly related to the velocity, right? The faster you fall through the air, the more drag you get, right? And we can even attach other things to it. Like what if there was a spring? What if we attached this ball to a spring, right? Here. So there was a spring force also. Let's call this like an F spring. And what if we said that the spring force, F spring, was like related to the amount of deflection, right? How far away you move. So it's some spring constant times x of t, right? Well, how does this change? Well, we come back here to F is equal to ma, right? Now our forces on the left side get a little bit more complicated, right? It's now mg, right, minus the force from the aerodynamic drag, right? Minus b x dot of t, right? Minus the spring force, right? Minus k x of t is equal to the mass times the acceleration, right? And again, now we see this is now getting a little bit more interesting. This again is still our second order, luckily linear ordinary differential equation. But now we can't go through the simple integration process anymore. This is not the right answer any longer for the position, right? This is no longer valid. So we're going to have to explore different techniques to solve this differential equation, which is what we're going to do in subsequent videos. I just wanted to show that this can get more and more complicated, even for this simple example of dropping a ball. In fact, you know, here I'll show you a movie of this. Is actually a cool system that that I use for students at the University of Washington in a controls lab, where we're basically looking at a ball like this, but instead of having a spring here that is keeping the ball up and down, we're actually using an electromagnet here. So, and that electromagnet, that spring force is very complicated. That magnet force, it's not just linearly related to the position, and it's something to do with how much voltage you pass through the electromagnet. So, long story short, this little simple example of just a ball moving up and down vertically in air can get complicated and can turn into nonlinear, linear or nonlinear ordinary differential equations. And again, we're going to talk about that more extensively in some of the subsequent videos. Okay, let's go take a look at another example of where you might see ordinary differential equations in physical systems. All right, so here's a system where it might be interesting to see if we can model this using ordinary differential equations. So I've got a quote-unquote two-tank hydraulic system. Of course, these tanks are just PVC tubes because that's all I was able to find in my garage. But what we want to do here is I filled them up with water, and I'm going to pull the plug, and I would like to know how is the height of water in tank 1 and the height of water in tank 2, how do those change over time? So for example, if I pull the plug here, right? Unfortunately, you can't see the height of water in the tanks, but as you can imagine, they're probably dropping down as water flows out. Now, what makes this interesting is, what if I were to say introduce flow into one tank? So now I'm increasing the flow rate into this first tank. How is the height of this first tank and the height of that second tank evolving over time? And as you can imagine, it's not a very simple, direct relationship. And actually, I think if we go and jump back over the board, we're going to see that you could actually model this system using an ordinary differential equation. All right, so here's that two-tank system that we just looked at. And what's interesting about this is, again, if you write the, quote-unquote equations of motion for the fluid flow in these two tanks, you'll basically get these expressions, right? This is an equation describing the time rate of change of the fluid height in tank number 1. And here's an equation for the time rate of change of the tank height in fluid 2. So, and again, what's interesting is if you look at this thing long enough, right, it's basically a linear differential equation. So here you have an H dot equation, and everything else over here is basically, these are all constant coefficients, but you see these independent variables H1 and H2 show up in this expression. And similarly, the height of tank 2, it matters, or the time rate of change of the height of tank 2, it matters on the current height of both tank 2 as well as tank 1. So both of these, this is actually kind of interesting behavior because it shows that these differential equations are what are called coupled, right? This first differential equation can't operate independently of the second one and vice versa, right? Which again makes sense because these two tanks are connected via this pipe. So the height of one affects the height of the other, and back and forth we go. So again, this is actually an interesting case where you see these differential equations show up in different areas of engineering and science that you might not expect it to. So I think those are two, pretty fairly simple examples. We will cover this a little bit later when we start talking about constructs such as state space representations, but that's getting a little bit ahead of ourselves. What I do want to kind of whet your appetite about is, as we go further and further down the road, you're going to see that, yeah, this differential equation discussion will take us very, very far. In fact, here's an example. If you stick with us, eventually we're going to get to the point of using ordinary differential equations to model entire systems like 6 degree of freedom aircraft simulators, and we'll be flying this around in computer simulations, solving them numerically on the fly, heck, maybe even interacting with these models in real time using a joystick. And again, the thing that underlies all the theory and the mathematical foundation for this is this idea of ordinary differential equations. So I hope you're as excited as I am to start on this discussion path. With that being said, I think maybe now might be a good spot to actually jump over to the slides, and let's look at some of the topics of how we're going to go about tackling our investigation of ordinary differential equations. All right, so here's the roadmap for our ODE discussion. So as we're doing right now, this is our introduction into ODEs, but then immediately following this, I want to look at how do we solve ordinary differential equations using what's called the Laplace method. So we've got a whole series of videos showing this workflow and talking about the strengths and benefits and why you might want to look at solving ODEs using the Laplace method. After that, we're actually going to kind of take a step, I guess in some senses it might be a little bit backwards, but after looking at the Laplace method, which I think is the good way to solve ODEs, we're going to look at a traditional way to solve ODEs. So we're going to look at both linear homogeneous and linear non-homogeneous ODEs, and we're going to be able to compare and contrast using the Laplace technique versus these quote-unquote traditional methods. Once we see both of those, it's then time to talk about standardizing our analysis into ODEs and looking at standard second-order differential equations. After that, that's actually going to allow us to set the stage for some more modern ways of analyzing ODEs. So namely, this is talking about writing ODEs using what is known as state space representations. And this we're going to see is if we understand what a state space representation is and how to solve it, it actually is going to allow us to solve an arbitrarily large system of linear ordinary differential equations. So that's incredibly powerful. And after that, I think we'll have a good understanding of sort of the theory behind ODEs. It might be fun to talk a little bit about working with ODEs numerically, meaning maybe if you don't have linear ODEs, or if you have linear ODEs that have interesting or complicated inputs, how could you solve those numerically using a computer tool like Simulink and MATLAB? So that's our game plan right now. That being said, this may change in the future. I may add or subtract videos to this discussion. So what I'm doing is I have an entire playlist full of all of the discussions in the appropriate chronological order on the YouTube page. So just go to my channel here and look for the ordinary differential equations playlist. And if you just start from the top going to the bottom, we'll hopefully hit all of these topics in an order that makes sense.
All right, so there you have it, our roadmap for ordinary differential equations. And as you can see, it might look like a long journey ahead of us, but it's going to be an exciting one. We're going to be learning a lot of new things, and we're going to see how these apply to not just to ordinary differential equations, but a lot of the concepts we're going to talk about now extend to a lot of different areas of mathematics and engineering, like numerical simulation, partial differential equations. All this, this entire world opens up once we start with this foundation of ordinary differential equations. So let's jump into it. And with that being said, I think this is probably a good spot to end this current video, which again, we were just trying to talk about ordinary differential equations at a very high level and just introduce the concept. And we're going to dig into the actual meat and implementation of a lot of these concepts in the subsequent videos. So I hope you enjoyed the video today. And if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just scroll a little ways down, click on that subscribe, maybe hit the like button, leave a comment. All of this really helps me continue making these videos in the future. And remember, new videos come out every Monday, so I hope I will catch you at one of these future discussions and we can all learn something new together. So until I see you again, I'm going to sign off for now. Talk to you later. Bye.